In the last video, we said that a proof is an essay that incontrovertibly shows that a statement is true, meaning that if a proof is well written and a reader accepts the starting assumptions, then there is no way for the reader to disagree with the conclusions of the proof. But for this to work, we need to establish our starting assumptions. Any formal system in mathematics rests on a set of axioms, the basic assumptions that we all agree are true. And so axioms can absolutely be questioned, but if we accept the axioms, then we have to accept any proof that is built on top of them. I'm going to give a set of starting point assumptions for our proofs in this class, but it's worth noting that these are by no means the most fundamental axioms one could choose. It is absolutely possible to break these down even further to even simpler starting points that have to be assumed. But we are using this set of assumptions because they provide a convenient starting point for this class, and because hopefully they are already familiar from your previous math studies. We have the set of integers. We have the set of natural numbers. We have the set of rational numbers. And we have basic mathematical operations that can be performed on integers, natural numbers, and rational numbers. So we have addition, subtraction, and multiplication. When we apply those on any two integers, we get another integer. When we apply those on any two rational numbers, we get another rational number. And if we add and multiply natural numbers, we get another natural number. Appendix D in the textbook lists all of these and a number of other things that you may assume in any of your proofs throughout the semester without proving them yourself. And even though I started out by talking about the foundational axioms that we build our proofs on top of, it's worth noting that these would not classically be called a set of axioms. Even though they are fundamental assumptions we are making, it's quite possible to derive some of these assumptions from others with careful proof writing, but we are not going to dig deeper than this in this class. At some point, we have to draw a line and say, this is our starting point. To try and dig deeper and define the natural numbers as a subset of the integers and then prove closure properties of the natural numbers is an interesting exercise, but beyond the scope for this class. If that sounds exciting to you, I recommend taking a course in set theory. Beyond our foundational assumptions, it will help to add some definitions to help us talk about the sorts of objects and operations that we want to investigate. Over the course of the semester, we will see lots more definitions to establish things that we want to do or things that we want to talk about, but here are a few basic ones to get us started. So here we are giving a precise and unambiguous definition of what it means for an integer to be even in terms of the set of integers and the multiplication operation that we already have from our foundational assumptions. And we can define an odd integer similarly. We can also define divisibility. There are also lots of synonyms for divisible by. We could say that B divides A, or B is a factor of A, and we have the notation for divisibility, which may be unfamiliar, that B vertical line A which reads as B divides A, and is equivalent to saying that A is divisible by B. We can, of course, build definitions on top of other definitions. For example, using divisibility, we can define prime and composite numbers. So we've used the notion of a divisor from our previous definition to help us establish the definition of a prime number. And we can define a composite number also in terms of our previous definition. It's worth noting that this definition of prime numbers only allows positive prime numbers, and there are some contexts in mathematics where it makes sense to allow negative numbers within the definition of prime, but we will follow the example set by our textbook, and for this course only allow positive numbers to be prime. Now that we have some definitions, we'd like to use them to make and prove some statements about the world. So in declaring statements about the world and then proving those statements, we will be establishing theorems. We'll see lots of synonyms for the word theorem, including claim, fact, lemma, property, but all of them boil down to statements that we will prove. And a common structure for a theorem is an if-then statement. An if-then statement has the form if proposition A, then proposition B. For example, if x and y are even integers, then x plus y is an even integer. This is a declarative statement in if-then form, and if we prove it, we will have a theorem. But I could also make if-then statements that would not be true. For example, if I replaced even with odd in this statement, then I would have a declarative if-then statement, but one that is not true. So then how do we go about proving that some if-then statements are true and others are not? For an if-then statement, we have two propositions that can both be either true or false. So let's make a table of all of the possibilities for these propositions and think about, for each case, is the if-then statement true or false? For this statement, it might be hard to think of examples for all of the possibilities because this statement is one that we intuitively know to be true, and so thinking of examples where the proposition is false might be harder. So let's instead think about an if-then statement that could be either true or false. The claim that if it rains tomorrow, then I will bring an umbrella is one that we can imagine being either true or false. So first, let's identify the propositions. A is rain happening tomorrow, and B is me bringing an umbrella. So let's think about each of the possibilities. Suppose that it in fact rains tomorrow, so A is true, and I do in fact bring an umbrella tomorrow, so B is true. If it did rain and I did bring an umbrella, then we would say that this statement is true. What about the case where A is true and B is false? That means it does rain tomorrow, but I don't bring an umbrella. Then the statement that if it rains, then I will bring an umbrella must be a false statement. What about the cases where A is false? So there we are saying that it doesn't rain tomorrow. Well, in that case, we have no evidence about this statement because we were only saying that if it rains, then I will bring an umbrella. And in those cases, we say that the statement is vacuously true. In the event that it doesn't rain tomorrow, then whether I bring an umbrella or not, I can claim that this statement is true. If it rains, I bring an umbrella. And in the case where A is false, there's no way for you to falsify my claim. If-then statements are another case where there are many equivalent ways of saying essentially the same thing. So let's list a few and think about how they're related. We started out talking about statements of the form if A, then B. And by filling in these blanks appropriately with A and B, we can get equivalent statements. But the phrasing of these statements and the order in which we place A and B is very important to their meaning. So let's think about how each of these statements relate in the following example. Here we have an if-then statement that hopefully gives us some intuition about the relationship between the propositions A and B. So our statement that if I got the job, then I must have filled out an application is equivalent to saying that I got the job implies I filled out an application. So here we can fill in A implies B is equivalent to if A then B. And now I'd like you to pause and take a moment to think about how would you fill in each of the remaining claims so that they match the claim if A then B semantically. For me it helps, as I've already done out loud once, to fill in must have in filled out the application. So whenever I got the job, because just like this sentence, we are saying that the only way I could have gotten the job is if I filled out the application. So here we have whenever A, we have B. Is sufficient for is saying that it is sufficient to know one proposition in order to conclude the other. So if we know that I filled out the application, is that sufficient to tell us that I got the job? No, I might have filled out the application and not gotten the job. But if I got the job, is that sufficient to know that I filled out the application? Yes, that's the only way I could have gotten the job. So A is sufficient for B. Again, filling in our proposition, in order for me to get the job, it's enough that I filled out the application. That doesn't follow. But in order for us to know that I filled out the application, it's enough to know that I got the job. That is a reasonable conclusion. So in order for B, it is enough that A. I think this example is a good one for understanding necessary. It is necessary for getting the job that you fill out the application. So we have B is necessary for A. And this last one is for me the trickiest. Blank only if blank makes sense in this context, but I always have a little bit of trouble sorting that out with our starting point. So let's think through it in this example. I got the job only if I filled out an application. That makes sense. I filled out an application only if I got the job. That's not usually how it works. So I got the job, A, only if I filled out the application, B. So all of these statements are equivalent ways of stating an if-then proposition. And for all of these, we use the following notation, which you can read as A implies B. So where does all of this leave us in terms of how to prove an if-then theorem? For an if-then statement, A implies B, we call A the hypothesis and B the conclusion. To prove an if-then theorem, we can show that when the hypothesis is true, the conclusion is also true, meaning that we are never in the case where the statement is false because A is true and B is false. So we go about proving this by first assuming that the hypothesis is true and then showing that this means the conclusion must also be true. In the case of our even integers claim, assuming the hypothesis would mean let's assume that we have two even integers, x and y. So our goal then is to assume that the hypothesis is true and use that to show that the conclusion must also be true under that assumption. And so by showing that whenever we are in the hypothesis is true condition, we are also in the conclusion is true condition, we have ruled out the possibility that the statement could be false. And this leads us to our first proof template of the semester. So because we are assuming the hypothesis and using it to eventually show the conclusion, we can begin by writing the hypothesis at the top of the page and the conclusion at the bottom. With our hypothesis and our conclusion laid down, our goal now is to connect them, and a very good way to start is to unravel the definitions, to lay out what does it really mean for x and y to be even integers, and what does our conclusion really mean when we say that x plus y is even. Since our hypothesis assumes that x is an even integer, we can state the definition of an even integer in terms of x, and that gives us this other quantity a that is half of x, and we can do likewise for y. Similarly, for the conclusion, where we are trying to show that x plus y is even, we can unravel the definition of this being an even number. And now our goal is to show that these assumptions result in this conclusion, which we can do with some very basic algebraic manipulation. And now we can connect this with our unraveled definition at the bottom, and we've completed our proof. At this point, we should go back and clean up our sentence structure and make sure that everything flows clearly and precisely, but we have used the template in order to get a proof of an if-then theorem. To fully hammer this home, let's point out that this top line of our proof is step 1 of the template. This bottom line is step 2. Unraveling definitions for step 3 got us this and this. And when we finished unraveling definitions, our gap was quite small, and so we were able to find operations to connect our facts from the hypothesis to the required facts for the conclusion. So we now have some basic axioms to build on, some definitions that let us describe our claims, and a proof template that we can use to turn our claims into theorems. That's all for now. I'm looking forward to seeing you in class.